Hi YouTube, this is Brendan. What I have for you today is a video that's very common when going over Newton's laws and maybe kinematics in an entry-level physics course, AP Physics, Honors Physics, or even IB Physics. So what I'm going to do is take you through this problem right here. It's a long one, it's really a lot of problems in one, but it's a very common grouping that physics teachers like to present to students. So what we have here is a box which is initially at rest on a horizontal floor. So I'm just going to start by drawing that situation. Here we have a horizontal floor, close enough. And we're going to have a box that is placed on that floor. And there's a box. Now, one student begins to pull the box directly to the right with a force of 250 newtons. To show that, I'm going to draw an arrow coming out of the box. Imagine this is a rope, and the student is pulling that box with 250 Newton force. On the other side of the box, we have student A's nemesis, who is pulling the box to the left with a force of 150 newtons. Now notice I did draw the arrow on the 150 Newton force at a shorter length than the 250 Newton force, and we commonly do that to just represent the magnitudes or the relative magnitudes. We also then state that the box weighs 20 kilograms, so I'm just going to make a note of this over here, that the mass of our box is 20 kilograms. And then we get to step one. So the first part of the problem is asking us to draw a free body diagram of the forces acting on the block. You can draw the free body diagram directly on the block, or you can draw it off to the side. I'm going to choose to draw it off to the side in this case, but it really doesn't matter. Your teacher may or may not have a preference though. So for the free body diagram, we represent our block as a specific point. Coming out of that block to the right is the 250 Newton force that is exerted by our first student. So I'm going to call this the force of A, 1. So that's applied force 1. On the other side, I'm going to have the applied force 2. And then we know that there must be two other forces on this box because gravity is always acting, assume the box is on Earth, and gravity always acts with a force of Fg. And anytime two things are in contact with each other, there's something called a normal force. The normal force basically acts to resist the motion that would otherwise happen if the normal force wasn't there. So this block is sitting on a table, but the block isn't falling through the table, which means that force of gravity must be canceled out because this block is not accelerating. So we can draw that as the normal force right here, which happens to be equal in magnitude and directly opposite the force of gravity. These are not reciprocal forces, keep that in mind with Newton's third law. However, they do cancel each other out, and we know that they cancel each other out because the box is neither accelerating upward nor downward. Alright, so that's our free body diagram. Now, if we wanted to figure out the net force on the box, the net force is the summation of all the forces. It typically makes sense in physics to break your forces down into forces that are acting in the y direction and forces that are acting in the x direction. So what I'm going to do over here is I'm going to say, okay, I have my summation of forces in the y direction, and I also have my summation of forces in the x direction. In the y direction, we have two forces, which are the force of gravity as well as the normal force. And in the x direction, we have two forces. We have the applied force and we have the other applied force, which we call A1 and A2 respectively. Now, in the y direction, these forces cancel out completely because it's a horizontal surface and the force of gravity acts straight down. The normal force, which acts perpendicular to the horizontal plane, is acting straight up. And it's not accelerating into or up above. It's not going down and it's not going up. It's only going side to side. So since it's not accelerating, in the y direction, we know that these two add up to 0 in this case. So we could say that the normal force is equal to the negative force of gravity. Now in the x direction, these don't cancel out because these are unequal forces. We actually know the values of these. So our applied force 1 is 250 newtons, which I'm going to say is positive 250 newtons because it's acting to the right. And our applied force 2 is acting directly to the left, and that is negative 150 newtons. So we can see that our summation of forces in the x direction is going to add to 100 newtons. Now, if there were a y direction and an x component, if they're both components of force, we would have to figure out the resultant force to figure out the net force. And you do that using the Pythagorean theorem. However, here, the summation of the forces in the y direction is 0, and the summation of forces in the x direction is 100. Since there's no y component, we can just say that the net force in this case, F net, is equal to F of x, which would be 100 newtons. And that's basically all the forces that are going into this one. Question 3 then asks us, what is the acceleration of the block? Well, we know the net force is what determines the acceleration because the net force is acting to the right. So here I could say 100 newtons in the positive x direction. We know that our acceleration is going to take the same directional value. If I'm pushing something to the right or pulling something to the right, it's clear it's going to accelerate in that direction. So what we use to figure out the next part is we use F net is equal to ma. So the net force in this case is 100 newtons in the positive x direction. The mass of the block is 20 kilograms, and we can solve this for acceleration in order to answer question 3. So we say 100 newtons is equal to 20 times a. Solving this for a, we would find a is equal to 5 meters per second squared. I'm not going to go over the units in this one, but acceleration does have units, meters per second squared. And that's how we could figure out the acceleration. Now, once we have the acceleration, we can move into this fourth question, which is how far has the block traveled 20 seconds later? This is a very common kinematics problem, something that is normally covered before Newton's law, so you should be familiar with this type of question at this point in time. When you choose to solve kinematics equations, you want to first write your key variables, in this case v initial, v final, delta x, a, and t. I will make a quick note here that if you're taking IB, v initial is often written as u, and delta x may be written as s. But if you're not, don't worry about that. Just pay attention to what's on the right side of that list there. So what we know, if we go back to the question here, is we can figure out some of these values. So the first one we can figure out is a box initially at rest. Well, if it's initially at rest, it's not moving, and therefore we know its initial velocity is 0. The final velocity, we're not given any information that we can use to figure that out at this time. We did, in the previous part of the question, determine that our acceleration was 5 meters per second squared. I put the units here. Everything's in standard units. Sometimes you'll have to convert. That's not happening in this case. As far as the time goes, the question's asking us how far the block has traveled 20 seconds later. So we can see pretty clearly that the time would be 20 seconds. Okay. Once we have 3 variables, we pretty much have enough information to solve for the other variables. Here we are trying to figure out how far the block has traveled, so that is the distance. And we're also trying to figure out what the block speed is. So we're both trying to figure out V final, as well as X initial. And to figure these out, we turn to our big five kinematics equations. In order to figure out delta x, I'm going to use the equation delta x equals v initial t plus 1/2 a t squared. And we can go ahead and plug in the values that we have. So v initial is 0, so this first term is actually going to conveniently just cancel out for us. And we're going to have 1/2 times 5 times 20 squared. Just plugging this into a calculator or writing it out, we would have 1/2 times 5 times 400, and 1/2 of 400 is 200, times 5 is going to give us 1,000. So this block has traveled 1,000 meters in the first 20 seconds. After this, we're going to look for V final. So this would be question 5 right here. And again, we can just turn to any one of our big five kinematics equations. Since I now have delta x, I like this one, so I'm going to use V final squared equals V initial squared plus 2a delta x. V initial is again 0, so fortunately this term just crosses off. 2 times 5 times 1,000, and this would be V final squared. So V final squared equals 10. 10 times 1,000 is going to be 10,000, and then we square root both sides, and we would find that our final velocity is 100 meters per second. So I'm going to go up here, and I now know that this is 100 meters per second. Okay, so that makes sense. So just kind of a quick check to see if that works, and it does. Now, the final question, question 6, is this situation realistic? So what we first want to do is kind of ask ourselves, is the force that the students are exerting on the box realistic? All right, so one student is pulling with a force of 250 newtons. The other student is pulling with a force of 150 newtons. A good way to kind of check yourself if that's realistic is how many kilograms would someone be picking up? Well, assuming that the force or the gravitational constant g is 10, 250 newtons would correspond to 25 kilograms of mass, and 150 newtons would correspond to 15 kilograms of mass. So it's about, I can't remember off the top of my head, maybe it's something like 40, 50 pounds. It's definitely a weight that someone could pick up. It would be heavy, but this would be a possible amount of force for making a high school student to be able to pull. It'd be heavy, but it wouldn't be impossible. Okay, so we have that. And then when we get to the final two answers here, we can see that the student has traveled 1,000 meters. All right, so of course someone can travel 1,000 meters, but can they travel 1,000 meters in 20 seconds? So imagine trying to run the length of 10 football fields in 20 seconds. Probably not going to happen, even if you're Usain Bolt. I'm pretty sure he runs the 100-meter in about 9 point something seconds. I'd have to check the exact time. But to run 100 meters in 9 seconds and running 1,000 meters in 20 seconds, it's probably not going to happen. And V final definitely isn't going to happen. 100 meters per second is suggesting that you can run not just the length of a football field, but a little bit longer, because a yard is a little bit shorter than a meter, in 1 second. So I would say that this problem is highly unrealistic. What might make it realistic is if these forces were only exerted for a couple of seconds or a few seconds, and the students weren't traveling 100 meters per second. So there you have it. It's a very common kinematics problem. It does not involve friction. Friction will make this problem just a little bit more complicated. But for now, I think this is a good intro into this topic. So I hope you find this video useful.